Alright guys, check it out. Number one, we're given the mass of a hockey puck. It's actually a little bit heavier than I meant it to be. I forgot to move the decimal place on that one. And we're given the force and we're given the distance. So to find the work, we can use work equals FD. Now to find the change in energy, well, the change in energy is work. That's the definition of work. Work is change in energy, so it's going to be the same number. If you doubled the force, that would end up doubling the work. You can also just input your own values to see what would happen, but it would end up doubling it. And if you double the force and then halved the distance, the times 2 and the times 1/2 would cancel each other out, so it would end up being the same as what your original value was. We're given the force that we are applying, and we're given a distance. Work is equal to force times distance. Now, if you double the force, you can go ahead and try that yourself. Oh, excuse me, I misread the problem. If we want to push it the same distance, and we're doubling the force, you would have to double the work in order to achieve that. So twice the work would just be 58,000. Okay, we're given the mass of a backpack. I'll abbreviate it using M sub B. We're given the distance, or the height of the cliff. Work equals force times distance. So let's stop here for a second. We got to think about what force we're dealing with here. I don't see force anywhere in the problem. So what am I going to do? Well, when you're moving something straight up and down, the force that you are dealing with, the force that you're counteracting, is the force of gravity. So if you're given the mass of something, then the force that you're dealing with you can find just by multiplying by 9.8. This is only if you're moving in the up and down direction. So we can also say that work is equal to mg times d. And that should look familiar to you. It should look a lot like the equation for potential energy. Potential energy is mgh. We use an h instead of a d, but it's the same thing. It's just displacement. So work and potential energy are the same exact thing. And if you look at the equation carefully, it's actually the same exact equation. Okay, let me stop here for a minute and catch up. So we plugged in our values. We found the work. The climber, we're going to do the same exact thing, except we're going to use 645 as the mass for her. So once we find that, we can add it to the work of the backpack to find the total work. Now we have this question again, what is the change in energy? The change in energy is work. It's the definition of work. It's the same thing as potential energy. It's the same thing as kinetic energy. They're all in joules. They're all the same thing. But this particular question is asking for the change in the climber's energy, so that's why I used the 5,300, because that's specifically for the climber. Alright, we have a boat that is being pulled at an angle. We're given the applied force, and we're given the distance. But I see something that's already wrong. The distance and the force are not in the same dimension. We have a force that's at an angle, and we have a distance that's straight along the x-axis. So we cannot use our arithmetic unless they are in the exact same direction. So what we have to do is put the force in the x direction only, so we can use our cosine function to achieve that. Now that I have my force in the x direction and the distance in the x direction, I can start working with my formulas. Work equals FD, so I plug in my numbers. Now we have the same question but for a different angle, so I'm just going to change that 25 to a 50. So you can see here something that you've experienced in your everyday lives. If you pull a rope at a really high angle, you actually accomplish a lot less work. Literally. Let me change my pen here for a second. This is the amount of work that you accomplish at a 50-degree angle, and this is the amount of work that you accomplish at a 25-degree angle. So you've all experienced this. When you drag your little brother to the Mardi Gras parades on his wagon, you want to pull that wagon with the lowest angle possible. You want it to be almost straight because you can accomplish more work for the same amount of force. If you have that wagon handle at a really, really steep angle, it's going to be a lot harder, and you're going to end up having to exert a lot more effort to apply the same amount of work. Okay. We have two people pulling a box at a 15-degree angle, so already there's a light bulb going off in the back of my head saying you're going to have to put this into its either x or y component. So let's take a look at how our distance is presented to us. Our distance is given in the y direction, that's the 15 meters. So if you want to use those forces, if those 225 newtons are going to be of any use to you, you better put them in the same direction as the distance, which in this case is the y direction. To put those values in the y direction, we need to use our cosine function. There's two of them, so don't forget to double it. And then we can just solve work equals FD, and we know both of those. We're given the weight of a suitcase here, and we have a staircase. We've got to find the work. Well, when you're carrying something up the stairs, the work that you're really achieving is just potential energy, mgh. I have the mg, that's the force, and I have the h, that's the 4.6. So we're good. And if you bring it back down the staircase, it's just going to be the opposite. So that 4.2 over here, that's just to throw you off. You don't have to actually make a triangle at all. You don't have to find the hypotenuse. You don't have to do any trigonometry. Back in the day, 2 months ago, you would have had to do all that. But now that we have these energy equations, it's way easier. If you're carrying something up and down, just solve for potential energy, and that's it. We have another rope at an angle, so I'm already thinking in the back of my brain, alright, I'm going to have to put this into either the x or the y component. Take a look at the distance. The distance is in the x direction. That means that you got to put your force in the x direction. We can use our cosine function to achieve that. Now to find the work, we can just multiply force times distance. Make sure you use your force that's in the x direction. We're given the force of gravity of a box. Given the time, we've got to find the power. Power is equal to work divided by time, or you can also say it's FD divided by time, because remember, work is equal to FD. So knowing that, let's plug in our values. To put it in kilowatts, you're just going to divide by 1,000. Oops, did I skip one? Let me go back. Here we go. Alright, we're given the distance, we're given a time, and we have a force. To find the power, let's do the same thing we did last time. Power is work divided by time, but we can rewrite that as FD divided by time because we know that work is equal to FD. Okay, now that I've found that, what happens if we move it twice as fast? Well, let's just actually plug in the right numbers and see what happens. Twice as fast would mean half the time. That's why I used 12.5 instead of 25. So it ends up being twice the power. Number 10, we got to do a little housekeeping first. We're given liters, but we don't want liters, we want kilograms. So we're given the conversion factor in the problem. We have our distance, we have a time, it's given in minutes, we don't want minutes, we want seconds. There we go. Now let's take another look at our power equation. Power is equal to work divided by time, or FD divided by time. But I don't have a force. What should I use for force? I don't see anything about a force in here. Well, you're pulling something straight up, right? You're pulling up water, it's a pump. If you're pumping water out of the ground, if you're lifting something, then the force that you are overcoming is the force of gravity. So the force that we're going to use is the force of gravity, which is mass times 9.8. We're given the power in kilowatts. Don't forget to multiply by 1,000. We've got to find the force. Let's write down our power formula again. I'm going to expand it out into FD divided by T. And let's just go ahead and rearrange this thing up front. Let's multiply both sides by T, and then let's divide both sides by PT. So now I have my equation for force. At this time I can plug in my values and solve. So here I have a force changing over time, and this is where you would use calculus, but we're not going to use calculus. We can accomplish everything that we need to do just with our geometry skills. So let's graph this thing. We have we're given force as a function of time here. So before we do anything, let's take a look at our units. If we took the area under the curve, we would be multiplying force times distance. Force times distance. That sounds really familiar. Force times distance is work. So if we can find the area under the curve, we will find the work, because the area would be force times distance, and force times distance is work. So, alright, let's go ahead and do that. Let's find the area of that top triangle first. That would be 1/2 base times height. And then let's find the area of that bottom little rectangle. That would just be base times height. Put them together, and then we get the total work. Alright, I hope that this was helpful.